Okay, we can begin. So welcome back. The plan for today is to continue our discussion of CMB, right? So remember at the end of last time, we were discussing hydrogen recombination. Okay, so we're thinking about, we're now well after the first few minutes when the primary elements were formed, but mostly we're left with hydrogen nuclei protons. We're not going to worry too much about the corrections from helium, but we're interested in the fact that we still have this plasma filling the universe. As we'll see, a very almost perfect plasma, so almost all of it is ionized. But as we cool and cool and cool, eventually electrons are going to meet protons and form neutral hydrogen. And the first step is we want to figure out when that forms, okay, when that happens. Okay, so we're just talking about these processes. Electron plus proton can form neutral hydrogen plus emission of a photon, and back and forth. And so long as this process is in thermal equilibrium, at the end of last time, we derived a formula for the fraction of free electrons in the universe as a function of temperature. Okay, this using statistical mechanics. So the electron fraction, called it Xe, is the number of electrons, that means free electrons, divided by the total number of electrons, which we can write like this. Number of free electrons plus the number of hydrogen, because they each house one electron. Okay, so that's the fraction of electrons of free electrons. And then last time, we derived the equation that Xe obeys, and it's this thing. We get all these funny factors here relating to the number density of photons that play a role in this process. Okay, that's the formula, the equilibrium formula for the number, and the EI here is 13.6 eV, is the ionization energy of hydrogen. Okay, any questions about this from last time? Okay, so this thing is the Saha equation. All right, so the good news is that this equation is simple to solve, okay, because we could just multiply both sides by Xe squared, and then you just get a quadratic. All right, so the solution looks like this. I'll introduce this factor F, where F is just this thing on the right-hand side. Just going to call that F instead of having to write that there. So it's an explicit function of temperature. And with all known prefactors, right? Obviously, we know the electron mass, we know the ionization energy of hydrogen, and then eta there, remember, is the baryon to photon ratio, 6 by 10 to the minus 10. So we know everything. Is that all right? So I'll just call that F. And then in the quadratic, yeah, I picked the plus square root because I know Xe has to be positive. So that's how I do that. All right, so you could just plot this thing, right? Just break out Mathematica and plot that versus temperature. And we can look at the answer and then double check that it makes sense. So here's temperature, again, or time, as I always like to plot it. Inverse temperature. Here's X. And for sure, it will start very close to 1. The hot universe is going to be an ionized plasma. And as at lower and lower temperatures, as we'll see in 1 second, it definitely goes like this and then comes down and heads towards 0. Okay, we're going to, let's just make sure we agree that it looks like that. Okay, so it has this shape. So to be sure that it has that shape, because this is a bit of a ugly thing to look at, let's just unpack F for a second. Okay, so roughly, if you ignore all your pi's and everything, factors of 2, F, let's just look at that. There's some sort of 3 critical parts of F, right? There's eta here, that's an extremely small number, so we want to pay attention to that. It's eta, right? This is the baryon to photon ratio. Which is like 6 by 10 to the minus 10. You can just say 1 part in a billion or so. And there's another very small factor here, which is this temperature over the electron mass to the 3/2. Okay. Now, we're going to see, we'll check in 1 second, but around here, there's a point here, which we're going to call the temperature of recombination, REC, which for convenience, we're just going to define as the point at which this is equal to 1/2. Okay, that's just a sensible definition. You would like to know when this occurs, so you can say what's the moment at which the ionization fraction of the universe is 1/2. And we call that the temperature of recombination. Okay, and from solving this equation, we can double check that this number will emerge in 1 second on the board over there. I'm about to write more stuff. This will be about 0.32 electron volts. Which, if you like, is about 3,700 Kelvin. This is the point at which Xe, as I said, is equal to 1/2. Okay, so we'll double check that we're 0.3 eV is when it does this. Okay, so let's just again look at this formula here. I want to write out what F is. So you have, say, a 0.3 or so eV, self-consistently, divided by the electron mass, which is like 500,000 eV. So this, don't worry about the pi's and so on. This is about 10 to the minus 6, this ratio, right? And then there's a 3/2. So, you know, this is like, yeah, let's write this as, well, let's just say T over ME for the moment, 3/2, and then this exponential. Okay, so in the vicinity of what we're talking about, if you're somewhere around here, F, this is going to be like, this is 10 to the minus 9 baryons to photon ratio. If T is in the ballpark of a few, like an eV or so, is 10 to the minus 6 to the 3/2, so that's another 10 to the minus 9. And then we have this exponential, which I want to keep. Is that all right? Yeah. Like in the vicinity of the region of interest, the T here I can estimate. The T here I don't want to estimate. It lives in an exponential, so I want to keep that explicit. This is a very rough estimate for F. Is that all right? And so you see, if you want to be near 1/2 here, you want X to be 1/2, by this formula here, I don't know what it is, F should itself be like 1/2 or something. Is that right? If you set that equal to 1/2, F is some silly number, right? √2 or something or other, right? If you set that to 1/2, you can check in your head whatever that is. Is that all right? So for F to be order 1/2, or so order 1, such that X is itself like 1/2, you see that you can read off this formula what the temperature needs to be without solving this directly on Mathematica. Is that all right? So in other words, so we have 10 to the minus 18, this exponential. So you need a gigantic exponential for f to be an order 1 number. Does that make sense? So f to be, say, 1 or so means the temperature has to be the ionization energy somehow divided by the log of 10 to the 18. That's our very rough, lazy estimate for the recombination temperature. Okay, so somehow you don't just get to the point where you're a little bit start to see the exponential. You have to be deep into the exponential to compensate the 10 to the minus 18. Okay, so log of 10 to the 18, this is 18 log 10, that's 18 times 2.3, that's about 40. So you see this is about 13.6 EV over 40, and this is our 0.3 EV or so, 0.32 EV if we do it properly. So naively, if you say when at what temperature, right, you have this gas of electrons and protons initially, and you ask what temperature at which the system will start to form hydrogen, let's say 50% of it becomes hydrogen. You know, if it was me, I'd say, oh, that's probably when the temperature is ordered the ionization energy, right? And T is order EI. But you see that estimate's not right because there's this funny, extremely tiny number out front. We're in part related to the fact that there's a huge number of photons in the universe. Okay, so even when your temperature is 13.6 EV or even half that, there's still so many photons available that can dissociate hydrogen and take it back to being ionized. So you have to wait till you're at even lower and lower temperatures. And so it ends up being that you have to drop by another factor of 40 in temperature down to 0.3 EV. So a slightly colder temperature than you would have expected. All right, questions about that? Okay, and then furthermore, let's just, I want to talk therefore about the shape of this thing. So I claim it looks like this as well. But because of that exponential, this is a rather rapid shape. Okay, it's very, very flat near 1, passes through a half, and then is very, very close to 0. So rather, it's an interesting function. It's kind of almost a step. Okay, so we can see that here by, again, if I go to my very rough estimate, little f, well, this one, I'll pretend the 18, whatever. Let's say you're at temperatures a little bit higher than the half here, which is the 0.32 EV. Let's say you went up to temperatures here of 0.6 EV, right? That's not much of a change, right? A factor of 2. But if you go up by a factor of 2 in temperature to 0.6 EV, a slightly earlier universe, now you have what? Well, instead of having this factor, this is like you need e to the 40 to compensate the 10 to the minus 18, you would have e to the 20, right? So that means this f is an extremely small number just by going up a factor of 2 in temperature. Right? You've got an e to the 20, which does not compete with 10 to the minus 18. So f is very, very, very tiny. Okay, and then we can summarize that. Okay, so when T is somewhat bigger, even a factor of 2 bigger than T recombination, F is tiny, exponentially tiny. And then you can go here, when F is tiny, what do you have? Okay, it's a bit annoying to stare at it like this. You would have to, you can, perhaps you can see, if you take the limit as F goes to 0 on this thing, X goes to 1. Is that clear? You have to think a little bit because the 1 there cancels the -1 there. And then what's left is 2F over 2F, which is 1. Okay. So X goes to 1. Okay. So X is actually within, up here, it's 1 plus an exponentially tiny correction in this regime. Does that make sense? And then the flip side of that is if we go to lower temperatures down here, even a factor of 2 lower, so down to, say, 0.16 EV, below my 0.32, now you have not an e to the 40, but an e to the 80. So F is now gigantic. Okay. And when F is gigantic, you can see what X is. So T somewhat less the recombination temperature, even a factor of 2. F is huge. Did I say that? Yeah, F is huge. Therefore, XE is now tiny. Okay, well, it's exponentially small. Is that all right? See, when F is huge, right, let's just be careful. When F is huge, you get X is 1 over root F. Tiny, for lack of a better phrase. Right. So it's a very dramatic shift. Okay, so it's almost, you could almost say sort of it's a kind of phase transition where you go from a hot ionized plasma state, and then you change the temperature a little bit, and suddenly it goes to a half, and then suddenly almost zero again. It's basically a neutral universe. All right. Any questions about this? All right. Maybe not to belabor the point, but let me just draw a picture in case it's not clear to anyone. Our picture is T bigger than T recombination. Our universe looks like this. Almost entirely ionized. And the moment we hit the recombination temperature, by definition, it means it's half free particles, half neutral hydrogen. And then even you drop by a factor of a few below that, it's basically all hydrogen. Any questions about it? Okay, so we can now ask the time of this process. So that is to say, what's the time at which the temperature is this 0.32 EV, the recombination temperature? Well, let's just think for a little bit. Let's just orient ourselves a little bit. So you recall, what's the time of equality in the universe? Remember the time of equality, matter radiation equality? You 40 something thousand years. Yeah, it's like 46, 47. Oh, yeah, we can write 47 or 50,000 roughly. Okay, that's matter radiation equality. And if we wonder what's the temperature at equality, so anyway, how would I compute the temperature at equality? Anyone have a strategy? How would I figure out the temperature of equality? Then remember the scale factor at equality? Yeah. 1 over 3,600, right. So if you recall, the scale factor, 1 over 3,600, that was matter radiation equality. And temperature, okay, you can just write as today's temperature over the scale factor, right? Temperature is redshift like 1 over A. It does, there can be a wrinkle in this, like when electron, positron annihilated. Remember, it boosts the temperature slightly, but that's only when there's some interesting transition like that, something that dumps its energy into photons. Okay, but that happened when the universe was like a second or so old, a few seconds. So after that, this is good. Okay, and there's no big annihilation processes that have happened since a few seconds. So we have this very simple formula, right? So we should always remember this. And T naught being today's temperature. Okay, so the temperature of equality then is just 3600 times today's temperature. Today's temperature is 2.7 Kelvin, which if you like EV, this is about 2.3 times 10 to the minus 4 EV, converting Kelvin to EV. And so this is about 0.8 EV. Okay, I just mentioned this as a reference, but recombination here is happening at 0.32 EV. Okay, so the universe is cooled even further than that. Okay. So that must mean that this process happens here when the universe is older than 47,000 years. And we have to get down from 0.8 EV down to 0.32 EV. So you can imagine this is another factor of a few in time. Okay, and we can compute this precisely. Let's recall something that we discussed in class a little bit and you did on the homework. If you want the time of something, you remember there's this integral representation that you studied on the homework. You can write an integral 0 to a. And then you fill it with these omegas. Whatever ingredients are relevant at the time, right? And I could add the dark energy, but that's negligible. Even when back to, we're going to be talking order a couple of 100,000 years. Back then, dark energy is completely irrelevant. So I don't need to add that to that. Remember this from your homework and so on. Okay. So you can just carry out this integral. And the reason I say that is because we're going to be a little bit beyond this time scale. As you go beyond this, we're going to be into the matter era. But it's not like radiation is completely irrelevant, right? At this moment, it's 50-50. We're going to find that the time is like a couple of 100,000 years or so when this happens. So it'll be, I don't know, like 75% matter, 25% radiation at that point, something on this roughly. You get what I'm saying? We're not that deep into the matter era. So you kind of have to put up with the full integral if you want to be at all precise. And then we just recall omega matter is about 0.3 today. Omega radiation today, 8.6 10 to the minus 5, right? Not much radiation left over today. And then we just need the A of recombination, which I can just invert this formula. That means the temperature of recombination over today's temperature. Okay. Today's temperature is this thing. 2.3 times 10 to the minus 4 EV. And the temperature of recombination, we said, is 0.32 EV. So that comes out to be 1400. So therefore, you can just compute the time by doing that integral. Is that okay? The integral, all you need to know is what scale factor you're interested in. The scale factor is 1400. Okay? This happened when the universe was 1400 times smaller than it is today. That's what that little exercise gives. Plug it into this integral. Is everyone with me? Sorry if the reasoning is a bit jumbled. Yeah. Ah, thank you. Very good. Thank you. 1 over 1400. Thank you. Did I mess it up? I probably, yeah, okay, I messed everything up. Okay. So this thing, thank you. Is everything okay now? All right, so you plug into this thing, all right. Just ask Mathematica to do it. And then you get the time of recombination. And that comes out to 250,000. Okay, so that's all we're doing, right? We're dropping, if you just look at it, when you convert between temperature and time, equality, remember, is temperature 0.8 EV, a time of 47,000 years. In order for you to cool down to recombination at 0.32 EV, you have to wait, that's a factor of 2.5 in temperature, so you have to wait a factor of a few in time. And okay, the factor is, we go from 47,000 up to 250,000. Okay. So if I, well, you good. We look at our favorite density versus scale factor times what? Here's radiation again, dropping like 1 over a to the 4. Here's matter. Right? Just the usual stuff from early on in the course. Matter redshifts like 1 over a cubed. I'm just reminding you here that equality is that point. The equality, 47,000 years for a temperature of 0.8 EV. And then you just wait a little bit longer. I don't know, the recombination, which is 250,000 years, a temperature of 0.32 EV. Okay, and then as I said, because this function, the fraction of ionization universe is this strongly dependent function on temperature, if it's stuck at almost 1, and then quickly drops to a half, and then you get very, very close to 0, in a rather narrow window on this scale here, around here, you know, once you're here, you don't have to be too far to the left of this line. You're ionized, and then the universe is neutral. Yeah. Oh, that's a good question. So there's a little bit of that, but there's a reason why that effect is quite small. Anyone tell me why that might be small? So yeah, you're right. We're looking at processes E plus T. So if we head in this direction, we release some photons. But does anyone tell me why this effect might be small in some way? You want to answer your own question? Yeah, the temperature at this stage is 0.32 EV. So these are not low energy photons relative to the typical photon. In fact, these are moderately high energy photons, a factor of a few. Yeah. That's right. Yes, so exactly. Right? Everyone follow that? We've got to always remember there's this baryon to photon ratio. So for every baryon, every electron or hydrogen, okay, let's say you're at 50-50, the same. Every one of these is a billion photons. So when this process occurs and you spit out a photon, that's an extra 1 on top of the billion. It's a little bit high energy. It's a factor of 40 or so higher than the other ones, but that factor of 40 doesn't compensate the factor of a billion. So it's a small little boost in the energy of the photons, but relatively small. But E plus E minus, back then, before E plus E minus annihilated, the number of electrons in the universe was like 3/4 the number of photons, these funny 3/4 factors from fermions, basically the same number. So that's a big impact when they annihilate with positrons. Okay, any questions about this? All right, so this is basically the fate of electrons in the universe and their formation into neutral hydrogen. But we do want to talk more actually about the fate of the photons themselves, okay, which I haven't even drawn here. So yes, we have for every one of these, there's 1 billion photons or so, but we would like to know what do they do during this process, okay, other than just say they scatter. So what we can be sure is that at this stage, the photons will be scattering like crazy off electrons. Okay, so even though at this high temperature, the neutral hydrogen is not forming, well, that's related to the fact that the photons are just scattering these things like crazy. So back here, you want to think this is a hot plasma. This is like the center of the sun, right? In the center of the sun, photons just bounce around like crazy. And they go on some crazy zigzag path. So here's the photon, meets this electron, this electron, this electron. We can scatter off the protons, but mainly electrons for reasons we can recap it in a minute. And so it just goes on some wild zigzag path, scattering very, very rapidly. Then over here, if you go to this extreme limit down here, photons almost don't interact with neutral hydrogen. Temperatures are actually getting low. So these are longer and longer wavelength photons that don't see hydrogen very much, and they basically freeze frame. So once you get that, those photons have a chance to propagate essentially forever until we put up our telescope and collect them. That would be the CMB. In a situation in the middle here where you have some ionization and only some ionization, now there's some chance that the photon will meet these electrons, but maybe it will, maybe it won't. And it's not that we cannot declare that this is the special moment at which photons will have a 50-50 chance. Is that clear? Just because the ionization fraction is 50-50 doesn't mean that the photon probability of scattering is 50-50. Those are two separate discussions. Does that make sense? I mean, it could be, and in fact, it will turn out to be the case, that just because the number of free electrons drops by a factor of 2, photons will still scatter like crazy off this picture here. We'll have to get quite closer to this picture. So we want to compute, there'll be some moment here in this history when the number of free electrons has dropped so much that the photon probability of scattering becomes small, let's say less than 50%. And then later it will be even less and less and less, and so it will just free shrink. Okay? So we want to know when that happens. Okay, so and when that happens, that's the moment we would say the CMB is essentially emitted. That's kind of like the moment at which the photon eventually gets to the surface of the sun and just free strings. We want to know the analog of when that happens in the early universe. Okay, so again, all of this stuff, this happened at 250,000 years. We're going to see that process is a little bit later than that. Actually, it'll be the 380,000 years is the time of the CMB. And let's just mention the equations that lead to that number. Okay, so this is the issue of photon decoupling. All right, so the basic process we're studying now is electrons plus photons just scattering. That's all it is. Whenever there are some free electrons, they can scatter like this. Or if you like to stare at a diagram, that means this. Time goes up. Anyone know the name for that kind of scattering? Someone said Compton. Yeah, it's Compton scattering. And we're going to be interested. Everything's around We're talking a few 100,000 years. We've already said we're down to temperatures of 0.32 eV. We'll be in that ballpark still. We have to double check. But at temperatures 0.32 eV, these electrons are very non-relativistic, right? Electrons have a mass of 500,000 eV. So when you're down to temperatures of a water an eV or half an eV or whatever, very much slowly moving electrons. Does that make sense? So electrons are non-relativistic at this stage. They're semi-relativistic at a second, so they're super non-relativistic by the time you get down to 250,000 years or so. And for non-relativistic electrons, Compton scattering has another name, if anyone remembers. If you don't remember, that's fine. Does anyone know what it's called if the electron is non-relativistic? Doesn't matter, but it's called Thomson scattering. That's what we're discussing. The formula is simplified. All right. And so the scattering rate gamma sub gamma rate for photons, gamma. So a photon has to meet an electron, so therefore this is set by the number density of electrons. Right? It's number density of the thing you scatter off times the scattering cross-section, and then the speed v. So usual formula for scattering rate. Yeah. All right. So v is 1. That's the relative velocity. So the photon, that means v is 1. And sigma, I want to call it sigma sub t usually for Thomson. And we can just write down the formula for that. Well, if we estimate it, just a recap of those things, what you would do if you want to be lazy and estimate it, you'd say that there's some factors of E here. So this amplitude goes like E squared, is like alpha, the structure constant. Right? Alpha is E squared over 4 pi, approximately 1 over 137. So that's the amplitude. And then the scattering cross-section is related to the amplitude squared. So this has to go like alpha squared. And then with non-relativistic electrons, it's only the electron mass that can set the units for the cross-section. So this has to go like 1 over m electron squared. That's the lazy answer. And then the right answer, when you do the calculation, is you get some 8 pi over 3 factor. All right. This thing, we write it out in electron volts, or mega electron volts, 2 times 10 to the minus 3 MeV squared. Or if you prefer, in units of regular area, this is about 8 by 10 to the minus 15 meters squared, the area. Cross-section is an area. Okay, so if you think about cross-sections, right, this is, you have a photon, you fire it, and you can think of the electron as having an effective area, this area, according to electromagnetism, set by alpha. So in some sense, if you fire the photon at that area, if it's on target, it will hit and scatter a lot. And if it's off target, it won't scatter much. So that's kind of an effective area of the electron. So that takes care of this stuff. Ne sigma sub t. By the way, when I write these angular brackets, I don't know if I mentioned it, but you're meant to do a thermal average. That's what that means. But this is really easy because V is 1 photon, And sigma was a constant independent of energy. So I don't have to average it. It's just a constant. Makes it very simple. Okay. So the only thing we have to worry about now is the number of free electrons. That's the big deal. So at early stages, this scattering rate is going to be huge because there's a huge number of free electrons around. So rest assured, this will be a big scattering rate. But then as our number of free electrons plummets exponentially, this scattering rate is therefore going to be super tiny because there aren't many electrons around. We have to think about that. Yeah, so that's really the big deal is to think about this NE. So NE, I can just invert it, write it as the fraction times the number of electrons plus the number of hydrogens. Inverted our definition. But if you think about it, the number of electrons here is also the same as the number of free protons. Imagining a neutral universe. So this is kind of the number of free protons plus the number of captured or protons bound in a neutral atom. So this thing in brackets is the total number of protons. Okay, and let's be lazy. Let's not worry about the fact for every proton, for every 7 protons, there's 1 neutron. Let's ignore the 1 neutron. Is that all right? So this is good enough for us. This is very close to the number of baryons. Okay with that? We're not worried about the 1 times 7 correction from neutrons. Although it's very interesting. Good. So now I'm going to write this as the number of baryons. I can write as the baryon to proton ratio eta times the number of photons. In this business, you have to play all these tricks. My God, why am I writing it in this complicated way? Well, the number of photons we know because the photons are thermal. So we know their number density is basically T cubed. More precisely, the number of photons, we've written it down many times, 2 zeta of 3 over pi squared times the temperature cubed. Okay. So even though that looks a bit funny, we now actually do have a concrete formula for the number of free electrons, which itself is a function of temperature. And we wrote it in terms of the fraction x, which is the explicit function of temperature we wrote on the board from the Sahar equation at the start of today's lecture. So we know exactly what that function is, some constants, and then T cubed. So it's an explicit function of temperature. All right, so you need to flesh that out. And then decoupling. What's our typical criteria for decoupling we've discussed? What should the rate be? What should we compare this scattering rate to? Right? It's always going to be something. You just multiply that by the Thomson scattering cross-section, you get the rate. What do I compare this rate to? It should be big or small compared to something or other. Now you want to think, you have this expanding universe. Are these photons actually going to meet this electron and scatter? What should that rate be compared to? Yeah. I'm sorry? Aha. Well, not the rate is so rate is 1 over time. It's inverse time. So the inverse, let's think about this, right? 1 over gamma is the time to scatter. Okay, the average time. These are all averages. So a photon might take a random photon. You have 1 billion photons, whatever, and you let them scatter. The average rate, or the inverse of the time it takes for them to scatter, will be 1 over gamma. Some will be a bit quicker, some a bit longer. Well, what if that time was longer than the age of the universe at the time? Doesn't sound very good, right? So the criteria for decoupling that we've discussed has been that you set gamma, a function of temperature, equal to Hubble, like the kind of figure of merit. Does that make sense? We did this criteria a couple of times already in the course. So we'll call this the temperature of decoupling, T decouple. Right? So in other words, if the rate were much bigger than Hubble, when gamma is much bigger than Hubble, it happens in the early universe, right? You can double check that this rate will be much bigger than Hubble in the early universe because the number of free electrons is huge and also has factors of T cubed that are also huge when the temperature is high. Then scattering happens easily. They would just on a very short time scale, they'll just meet an electron and scatter. And if you went to the other limit, where gamma is much less than Hubble, by the time the photon wants to meet an electron, the universe is doubled in size, right? If it's less than Hubble. The age of the universe is sort of order 1/h, right? It's like matter era, h is 2/3t. So there's some 2/3, but h is sort of roughly 1/t. So then you basically never scatter. Okay, and the boundary is when gamma is h. We can define that as the time of decoupling. Now, what's interesting about this is that you mentioned a half. At this level, a half is reasonable. Like I cannot necessarily say that gamma h is the sacred rule. What about gamma equals 2h or gamma equals a half h or 2/3 h? However, those differences in this particular case don't matter too much because our friend xe here is almost this step function. It's almost exactly 1, and then it's going to come down, it's going to plummet to be very, very close to 0. So if you change your criteria here just a little bit, it will change the T decoupling a little bit, but not much. Because this is such a rapid function of temperature. And we can double check by changing the criteria a little bit. And we can be more precise in 1 minute. Does everyone get my philosophy here? Okay, so we have gamma as an explicit function of temperature, right? You just have to spit out x from the Sahar equation, so it's a little ugly looking, but it's okay. And then Hubble, one way you can write Hubble is I could write h naught, square root this thing again, omega naught, a cubed, a4, right? Usual formula for include matter and radiation. But then, unless I put them upstairs instead of downstairs, this a cubed is t cubed over t naught t4. So there's h of t. All right. So you have everything. Okay, just set these to be equal, solve some algebraic equation with Mathematica, and you'll find T DEC for decoupling is 0.25 eV or so. And that corresponds to a scale factor of about 1/1100. Is that all right? I mean, you have to set them equal to each other. And once you have the scale factor, you do that integral to get the time associated with this. I'm not going to rewrite that. The time of this is about 380,000 years. This is a famous time at which the CMB is emitted. Everyone okay with the strategy? Now you get that, you take an inverse with respect to t naught to get a, do an integral, you get t. Now, if you want to be a bit more precise about this thing here, okay, other than the fact that I tell you, if you put a 2 here, maybe instead of getting, I don't know, 380,000, you might get 370,000 or something. It's not going to change things much. If you want to be a bit more precise, what you can define if you have a rate at which photons are scattering, which is a function of temperature or equivalently a function of time, we can go back and forth, and then you integrate that over time, right? dt, what does that mean? Okay, the rate of scattering times dt is the number of scatters that you have in time dt. What that means. So if you integrate this thing over some interval of time, right, that's the expected number of scatters you would have in that interval of time, the average, and the fluctuations. And so you can integrate this all to today from some time t, with a dummy variable. So this would be the number of scatters at time t from time t to today. Okay. So we have a photon today. It has not scattered for a long, long time, but if you go back in time, there was a time at which it scattered t, the time of its last scattering. Does that make sense? So you can set this thing, if you set it equal to 1, you can ask, when was the number of scatters? At what time? This would be called t of last scattering. You can just write t sub ls. T sub ls. And you could set that equal to 1. Right? So basically, these photons in the early universe are scattering like crazy, but then there will be a last scatter. And after that, it'll go all the way to today. By definition, it's the last scatter. So you can ask, what's the time at which you had that last scatter? Well, you would have to set this integral, the number of scatters equal to 1. And you can compute that, and you get a number very, very similar to this. Very close. Maybe differ by, I don't know, 5,000 or something years. Okay, so let's just say this is approximately t of last scatter as well. So yeah, so in some sense, it's a more precise statement. It's a very interesting thing. When was the last time at which it scattered? Just set that integral equal to 1. This is an average, and you could go to town, you can think about the probability distribution, when that was the last scatter. So this is like the mean, but the standard deviation around that is relatively small, like 20,000 years or something. Because if you go up in temperature just a little bit, there's a much more free electrons, so they're scattering like crazy. Go down in temperature a little bit, there are so few electrons now, the probability is very tiny. So you want to be very close to this time of last scattering, not too far away from that. Oh, okay. And what I should say is that the 0.25 EV that we get out of this little analysis here, so you know it is indeed in the ballpark of the 0.32 EV when the universe was half neutral. That was defined as the time or temperature recombination. But you might, again, you go from 0.32 EV down to 0.25 EV, it doesn't sound like much, but it actually does matter. Okay, if I go back to our plot of x versus time or temperature, here's x. It went like this. Here's 1 over t recombination at 0.5. Right, so this one is 1 over 0.32 EV. But as we've discussed, this curve here is plummeting exponentially. So even when you get down to just 0.25 EV, which is, you know, not too far over, it's just here. Okay. Well, I haven't drawn it very well, but you can check by just moving that, right? Remember, this was associated with it some factor of e to the 40 to compensate the 10 to the minus 18. So even if you change from 0.32 EV to 0.25, you know, now you're like, I don't know, e to the 50 or something, right? It doesn't take much when you change the temperature a bit in an exponent. So x down here, that number there, I didn't draw it very well, is actually much less than a half. And so if this is 1 over t decoupling, so 1 over 0.25 EV, this number here turns out to be about 10 to the minus 3. It's plummeting that quickly. Anyway, that's what you get from setting these equal or finding the moment of last scattering. But that solidifies the fact that the photon, how neutral the universe needs to be, right? 50% is not good enough. Photons love scattering off free particles, and the parameters are such that you have to get down to only this level of neutrality. Okay, only 1 part in 10 to the 3 is still ionized. So it's almost perfectly neutral. Then finally, the photon says, "Okay, I'm going to miss those residual free electrons." Okay. And then you wait a little bit more. The number of free electrons is ridiculously small down here. I should say, of course, it's not going to last forever. Way down here somewhere, our black curve is going to be wrong. It's going to rise up a little bit. Because at much, much later, what happens in the universe at much later that might deliver us free electrons? Sorry? Say again. A big rip in the future of the universe? Okay, maybe not too far into the future. That much, I'm not sure. We don't know. I meant something that within the last few billion years. Yeah.
Star formation.
Star formation, right. Yeah, if you wait long enough, stars will heat up and ionize their surrounding medium. So one has to be a bit careful to check that some of those regions might absorb the photons. So that's a more detailed thing. But let's just say at the end of the day, most of these photons do propagate through that and survive to today, the CMB. Okay. On time. Yeah. So again, I'll say it one more time, just to belabor the point again, perhaps. Temperature decoupling, or time much less than decoupling, which is 380,000 years. Photons are just going nuts, okay, scattering like crazy. And then at the temperature of decoupling, where the universe is mostly neutral by this point, is what I'm saying, down to 10 to minus 3, it's mainly hydrogen, but there's still an occasional electron and proton that I'm not drawing in the universe. Okay, maybe I should throw that in. Doesn't look too crazy. Oh, by the way, can anyone tell me why have I been focusing on photon scattering of electrons? Why don't I think about photon scattering of protons? I mean, I should. Is there anything we've discussed so far as to why I could just ignore that? I've always been dealing with photons of electrons. What about protons? Yeah. Well, that's not a bad argument, except I think if that's the argument, I should have put in a factor of 2, because I computed the rate of electrons. I didn't add to it the rate of protons. So I missed a factor of 2 then. Yeah. Exactly. The rate is proportional 1 over the mass squared. So the Thomson scattering is 1 over m electron squared. The proton version, which we should add, would be a correction of 1 over m proton squared. There'd be a correction of 1 part in like 1800 squared, right, from the ratio of the proton to electron mass. Or stated differently, in classical physics, what you would just say is that what is this process? If you think of in the classical limit, we have a classical wave coming in, electromagnetic wave, and there's a charge sitting there, right? It causes the charge to oscillate, and then the charge re-radiates a wave. That's basically what this process is. But you can imagine that that's much more effective on lighter particles, which accelerate much more than the heavy protons that hardly accelerate at all. So they re-radiate a very tiny amount. So this is why we focus on the lightest charged particles, the electron. Okay, so anyway, at this point here, once we've reached T decoupling, basically means your typical photon has now come along, scattered off this one, and then that's it. It's going to go on its merry way. And so this is the CMB sort of emitted. And then at later times, these photons are just going straight through. All right. Yeah, and then you want to take, well, we don't have to do this exercise because we're going backwards. But if you think of starting from this point, you then want to redshift this till today. But rest assured, by my calculation, you will get T naught, the one that we started with. But just to be clear, you then redshift that till today, and you get the 2.7 Kelvin. That's the CMB. All right, maybe we can put every one of these numbers on the board that we've discussed in today's lecture and the last couple of lectures before we, well, I wanted to change topic, but maybe we'll save that for Wednesday. Okay, so let's summarize all these numbers that we've encountered. Timescales and temperatures. Oh, should never trust other people with their market. All right, that's why I bring my own. All right. So I'm going to list these events of interest from the sort of hot thermal universe down to this era. Okay, so one was neutrino decoupling. And then very soon afterwards, E plus E minus annihilation. And elements, nuclei at least, deuterium, not neutral atoms, but the nuclei, helium-3 and the most stable helium-4 formation, matter radiation equality, recombination, a photon decoupling. Okay, so putting in chronological order. Right. All right, time, just to remind you, decoupling for the neutrino is about 1 second. Okay. We talked about all these time scales. E plus E minus is about 4 seconds. In these form, we said something like 200 seconds or so. At least that's when deuterium became stable. You have to wait another minute or so for to get to helium-4, but that's okay. Matter radiation equality, we said it's like 47,000 years. Not a lot happens between there and there. And then recombination, in today's class, we got 250,000 years. And then the CMB or photon decoupling, 380,000. Okay, maybe we could add to this. And then not a whole lot happens after that. 9 or 10 billion years is when we get matter dark energy equality, and 13.8 billion is today, but I won't put that on this list. And just to convert that to temperature for you. So this is MeV neutrino decoupling, half an MeV naturally, or E plus E minus annihilation, the electron mass. Deuterium was forming a bit later, 0.08 MeV. That delay was the same reasoning that we had a delay to get down to recombination, is that there are all these photons that keep dissociating deuterium, and you have to wait a surprisingly long amount of time to the temperature is 0.08 MeV, even though deuterium has a binding energy of 2.2 MeV. There's a similar reasoning. Okay, then matter radiation equality is about this 0.8 EV. Yeah, went from M to E, big difference. And then 0.32 EV as we discussed for recombination, and 0.25 EV for CMB emission. right? And if we want scale factor, and let's write inverse scale factor, okay, or redshift. Equivalently, I should just say redshift. So 4 by 10 to the 9, we didn't mention these numbers, but neutrino decoupling is when the universe was 4 billion times smaller than it is today, if you think about it. 2 by 10 to the 9. Temperature just goes like 1 over A from essentially this moment onwards. So it's very simple to connect this to this. There's an 8-4 here. That's why those numbers are not quite factor of 100 of each other. 1400, 1100. Okay, those are the redshifts. And maybe let's just add one more tiny little thing. Just to remind you, recombination here means x is 0.5. And then here we found that x was like 10 to the minus 3. It's not defined as that, but it turns out to be that. Okay, that's our summary of the thermal history of the universe. Any questions about this? Okay, so going forwards, what we kind of care about now is again, going back all to the first lecture, all of this is going on, and even these microscopic processes, electrons scattering off photons, if you take a box, we still treat the average density in the box as uniform. Same as going on here is this box is this box is this box. We don't distinguish between what's happening in one box versus the next. So the density is the same. The number density is T cubed, or the energy density is T to the 4 for radiation. We don't say, well, the temperature over there is a little bit different than the temperature over there and so on. We've been ignoring all that. Okay? So we treat things like microscopically, of course, there are inhomogeneities. There's an electron there and not there, like the air molecules in this room. But you do a little bit of averaging, you treat it as uniform. So that's the thing we wish to not do anymore going forward. In other words, we wish to care about the inhomogeneities, which start off extremely small, as we discussed early on in the course, but they grow over time under gravity. So that's the key thing to discuss in the next couple of lectures. Okay, so we can go down that path starting Wednesday. But any other questions about this? All right, we'll see you on Wednesday. This one? Okay, I don't go to, okay, when I say temperature is much bigger than T decoupling 0.32 eV, I'm not imagining, okay, not that much higher than 0.3. So for example, I'm not even going up to half an MeV when I have to worry about positrons and so on. So think of this as maybe a factor of 10 or 100 bigger than that, but not a million or a billion times that. So I don't have any quark-gluon calcium at this point. Oh, sorry. Sorry, I missed. Um, you mean in terms of observations? You mean like a theoretical box? Yeah. If I go to temperatures, say, well above QCD phase transition, I could draw that box and be somewhat confident that it's correct. I would just scatter off nearly free quarks and gluons. Yeah, I think that would be all right. But yeah, we don't have a direct observable connected to that because, yeah, these photons end up being emitted at 380,000. So the memory they have, so to speak, of when they were scattering off quarks and gluons is just so washed out by that point that we don't have an observable. So the neutrino decoupling would be an observable at about a second, but we don't have a direct observation of that. Although there's some out there, out of the box ideas to try to observe something connected to that.